In this video, we'll look further into the relationship between deterministic finite automata and sets of strings, arriving at the definition of regular sets, the study of which will drive our inquiries during this segment of the course. Let sigma be a finite alphabet. We'll use the alphabet 0, 1 in our examples for this video, but the concepts and results we discuss apply to any finite alphabet. We've already seen what a deterministic finite automaton M over sigma does. For each input string x in sigma star, M either accepts x or rejects x, thereby figuratively coloring each string in sigma star green or red. We define the language accepted by M, denoted L of M, to be the set of all strings that it accepts. Please note that if M is a DFA and A is a set of strings, the phrase M accepts A means exactly that L of M equals A. This doesn't mean just that M accepts each string in A, in other words, that A is a subset of L of M. It means that these are the only strings that M accepts. In our example, the individual strings 0, 1, and 1, 0 are accepted by M. But we do not say that M accepts the set 0, 1, 1, 0 because there are more strings that it accepts, not just those two. This connection, that each DFA M over sigma gives us a subset L of M of sigma star, distinguishes certain subsets of sigma star as special. We call a subset A of sigma star regular if there exists some DFA M over sigma that accepts it. This definition directly tells us how to logically handle the statement that a set A is regular. If we're given a regular set A, we can conclude that there exists some DFA M accepting that set. On the flip side, if we want to show that a set A is regular, we can construct a DFA accepting the set A. Regular sets will be a significant topic in this course, so let's start with some simple examples of regular sets. At this point, our only means for proving that a set is regular is to construct a DFA that accepts it. Let's use this to give our first few examples of regular sets. It's easy to design a no DFA n over sigma that rejects every string. Just make none of the states accept states. This can be done with just one state, the start state, and making that a sync, but not an accept state. What's the language accepted by this DFA? Well, no matter what string we input into this DFA, n rejects that string. So the set L of n of strings accepted by this DFA is the empty set, giving us our first example of a regular set. Making that single state an accept state instead gives us a yes DFA y that accepts every string in sigma star. This means that the set sigma star of all strings over sigma is also a regular set. We saw the DFA shown to the right in our first DFA video, and we determined the set that it accepted is the set 0 to the m, 1 to the n, where m and n are greater than or equal to 0. This set is thus, by definition, regular, and it gives us our first non-trivial regular set. So far we know three examples of regular sets: the empty set, the entire set sigma star, and the set 0 to the m, 1 to the n, along with, of course, the language accepted by any other DFA we can draw. Now, regular sets are a particular type of sets of strings, and we have quite a few set operations that we could use to build other sets of strings. A reasonable first question would be, which of these maintain this property of regularity? Complements? Unions, in other words, sums? Intersections? Products and powers? Asterisks? The answer, it turns out, is if the sets A and B are regular, then all of these are also regular. Our goal will be to prove all these results, but we'll need to introduce some new tools before we do so. The very first one, though, is already within our reach. If A is a regular set, then the complement of A, in other words, sigma star take away the strings in A, is also a regular set. The proof is straightforward. Suppose that A is a regular set. By definition, there is some DFA M that accepts the set A. Let's take the example of the DFA accepting 0 to the m, 1 to the n to illustrate. All that we need to do is modify M in such a way that rejected strings are accepted and vice versa. We can do this by toggling accept states, turn every non-accept state into an accept state, and every accept state into a non-accept state. The same could be done for any DFA, with the same effect of swapping the sets of strings that are accepted and rejected. The language accepted by this new DFA M bar will be precisely the complement of the language accepted by our original DFA M, that is, the complement of the language A. So by definition, A bar is a regular set because it's the language accepted by the DFA M bar. Let's review the basic line of reasoning in the proof we've just seen, as is an important process. We are given a regular set. By definition, this gives us a DFA whose language is that set. We modified that DFA to achieve some end, and the modified machine's language was the set we wanted to show was regular. Don't underestimate the significance of this result. That the complement of a regular set is regular is not automatic. It must be proven. But DFAs are simple enough to let us see exactly how to modify a DFA so that it accepts the complement of the set it originally accepted. But this will not be so simple. In fact, in some cases it will be impossible for other machines we encounter in this course. All this back and forth with arrows might remind you of functions, and taking a step back, this is exactly what's going on. We can think of L as a language function, mapping each DFA M to its language L of M as a subset of sigma star, thus giving a function from the set of all DFAs over sigma to the set of all subsets of sigma star. If you haven't seen the script P before, it's read the power set of sigma star. It's defined to be the collection of all subsets of sigma star. You can chew on that for a bit if you like, but for now it simply fills the role we need of it. Our language function L outputs subsets of sigma star, which are then elements of the power set of sigma star. The domain of this function is the set of all DFAs over sigma, and its codomain is the set of all subsets of sigma star, in other words, the power set of sigma star. This function's range, that is to say, the subsets of sigma star that it actually outputs, is precisely the collection of regular sets over sigma, because the definition of a set of strings being regular is that it's the language of some DFA. Regular sets were defined via this relationship, so this is also how we'll start reasoning about them. The interplay between languages and machines will be a theme throughout this course. In this video, we've seen how each deterministic finite automaton over some alphabet sigma gives us a subset of sigma star consisting of the string accepted by the DFA. We define such subsets of sigma star as regular sets, and this definition gives us our principal tool for showing that a set is regular, by finding a DFA that accepts the set. Our current knowledge of DFAs is enough to show us that the empty set and all of sigma star are regular, and that any complement of a regular set is regular. Two more concepts related to finite automata will give us the tools we need to show the rest. Products of DFAs will allow us to show that the intersection or union, in other words sum, of two regular sets is regular. And non-deterministic finite automata, or NFAs, will allow us to show that the product of two regular sets is regular, as well as the asteroid of a regular set. First, though, we'll take a look at regular sets from the perspective of strings.